Today's video is on Chapter 14, Heat and Heat Transfer Methods. So we have some really important examples to look at in this chapter, but we'll start out defining some terms. So heat is the transfer of energy due to a difference in temperature. So if you put an ice cube into a glass of water, the ice cube is going to melt, and in the process, the water will change temperature because of a transfer of heat energy. And there are lots of other examples, certainly, but that's a prime one. So heat energy is measured in calories or joules or BTUs. BTUs are the British unit. Calories are a CGS unit, and joules will be the one we will use in class. The only reason I bring up calories now is to remind you about what calories mean on a package of crackers or a candy bar. So 1 calorie, written with a small c, is the amount of heat energy necessary to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. You can convert that into joules and end up with 4.18 joules. That's sometimes called the mechanical equivalent of heat. But in food, and I've mentioned this in a previous chapter, in food, the calories you see on a candy bar or anything you buy, those calories are really kilocalories, or 1,000 of the little physics calories. And if you write it, you should write it with a capital C, not a little c. And I think I even mentioned in that previous chapter that if you buy a candy bar in a country that uses the metric system, the units on the back will not be given in calories like they are in the United States, but it will be given in joules. All right, and the BTU stands for British Thermal Unit, and that's the British system unit for measuring heat. And you can see it's defined in terms of a pound of water and a change in a degree Fahrenheit. And you can convert BTUs to kilocalories. So specific heat is a new concept for us. This is the amount of heat energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. And the formula that you need to know, you must know this, our formula relating heat and specific heat and change in temperature to mass is Q equals MC delta T, where Q is the heat energy required, and we'll measure it in joules. M is the mass in kilograms. Little c is the specific heat, and it's measured in joules per kilogram degrees Celsius. And delta T is the temperature change, and that's going to be final temperature minus initial temperature. To give you some idea about how specific heats vary, we have aluminum and stainless steel and copper and silver and gold. You've got the specific heats in calories per gram degrees Celsius. We're not going to use those numbers. We're going to come over here and use the last column where our values are in joules per kilogram degrees Celsius. And certainly there's a table in the chapter that lists all kinds of specific heats. So you can see aluminum has the highest specific heat, and as you go down the list, gold has the smallest specific heat. So let's talk about what specific heat means in terms of changing the temperature of something. And the best way I know to do that is with an example talking about a cooking pot. So suppose in our list of 1, 2, 3, 4, 5 metals, we want to know which one makes the most efficient cooking pot. Well, we would design an experiment where we would hold Q constant and M constant. So the pots would all have the same mass, and we would supply the same amount of heat energy to each of them. So maybe you'd take a little can of Sterno and light it and put the pot on top of the sterno flame. So we control Q and M, they would be constants. And the only thing that would change would be C, and what we want is, we want to find out how does that impact delta T. So the most efficient cooking pot would be the one with the largest change in temperature for us, the biggest delta T. So if you look at this, if Q is constant and M is constant and C varies, we want one that'll give us the largest delta T. So for delta T to go up, 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 but to keep this equal sign, if one thing goes up, another thing on that side has to come down or the equality isn't true. So if delta T goes up, 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 then little c has to come down, down, down. So what we want is the metal with the smallest specific heat, and in fact that is gold. If you look at your list, that would be gold. I saw a TV show one time where Julia Childs was cooking fish in a gold frying pan because she was talking about thermal conductivities and temperature changes. She also had guards on her studio set. Okay, so as specific heat comes down, delta T goes up if M and Q are held constant. So another way to write that out is to take that equation and say, okay, Q is constant, M is constant. What happens to the specific heat if delta T goes up? And you can see that the specific heat would have to come down. So to do some problems with this, we need something referred to as calorimetry. Calorimetry says that you want to isolate your system and you want to look at the amount of heat energy lost and the amount of heat energy gained, and they should add up to 0. Sometimes they, instead of having it equal 0, they put heat lost on one side and heat gained on the other. I have a problem with that because sometimes it's confusing to students to decide which one's gaining or losing heat energy. And if you put them both on the same side, then the delta T, the change in temperature, will take care of what gets lost and what gets gained. So let's do an example. That's, I think, the easiest thing. So we want to know what is the final temperature if 0.05 kilograms of copper at 50 degrees Celsius is used to heat up 0.3 kilograms of water at 25 degrees Celsius in a 0.1 kilogram aluminum cup. So when I do my table of knowns, finds, and formulas, I like to group all of one kind of thing together, or rather maybe not all of one kind, but all of the things that relate to a specific material together. So all of the copper numbers together, all of the water numbers together, all of the aluminum numbers together, because they have to go into the equation based on the material. So the mass of the copper is 0.05 kilograms. The initial temperature of the copper is 50 degrees Celsius. The specific heat of copper is 390 joules per kilogram degrees Celsius. And we're through with all the things we know about copper. For water, the mass of water is 0.3 kilograms. The initial temperature of water is 25 degrees Celsius. The specific heat of water is 4,186 joules per kilogram degrees Celsius. The mass of the aluminum is 0.1 kilograms. The initial temperature of the aluminum is 25 degrees Celsius. And the specific heat of aluminum is 900 joules per kilogram degrees Celsius. We are looking for the final temperature. And our formulas are that Q lost plus Q gained equals 0. And Q is equal to MC delta T. So heat equals mass times specific heat times change in temperature. And we remember that change in temperature is T final minus T initial. So what do? We set up our equation where we list all the Q's on one side and set them equal, the sum equal to 0. So we have copper and water and aluminum. So we're going to say Q lost plus Q gained is 0. So the Q of the copper plus the Q of the water plus the Q of the aluminum equals 0. The Q's will each be equal to MC delta T. So I'm going to have MC delta T copper plus MC delta T water plus MC delta T aluminum equals 0. And now you'll see I've done something a little odd. I have listed each of these on a separate line. Copper gets a line, water gets a line, aluminum gets a line. Why? Because all three won't fit on one long line. And I have discovered that when I try to put more than one thing on a line, I sometimes plug in the numbers in the wrong places. So I give each thing a line, and off to the side, I make a little note as to which item each line is in reference to. You do not have to do this. If you want to write all the way across, that's perfectly okay. You don't have to list out to the side what they're equal to. Notice I put colons beside them. You could, well, if I can get it to show up, you could put a little line if you wanted to. And in fact, I could, let's see, we can make it red, and we could, whoops, where are we? We could make it dashed. So I could make a little red dashed line so you'd remember that the copper, the water, the aluminum are on just their designators. All right. So filling in, M for copper is 0.05 kilograms. The specific heat is 390 joules per kilogram degrees Celsius. And delta T is T final, we don't know that, minus 50 degrees Celsius. And then you'll notice at the end of that line I have a plus sign because there are three terms in the equation, and this is just the first one. So plus those same things, but for the water. So 0.3 kilograms times 4,186 joules per kilogram degrees Celsius times T final minus 25 degrees Celsius. And then notice there's a plus. Now for the last term, it's for aluminum. So 0.1 kilograms times 900 joules per kilogram degrees Celsius times T final minus 25 degrees Celsius. And it will equal 0. So now what do we do? I have found that I make a lot of mistakes with these problems, not because they're difficult, but because they have so many little parts and that I have to write out every single step. So 0.5 multiplied by 390, and then 0.3 times 4,186, and then 0.1 times 900. That's going to be my next step. Again, I'm not going to put the little dash line down. You can if you want to or not. So 0.05 times 390 is 19.5. The kilograms will cancel and we'll be left with joules per degree Celsius. And then you notice we haven't done anything with the values in parentheses. So they get written down just like they are. It will be 19.5 joules per degree Celsius multiplied by T final minus 50 degrees Celsius. And then plus, don't forget the plus signs. 0.3 multiplied by 4,186 gives us 1,255.8 joules per degree Celsius. And then that's going to be, will be multiplied by T final minus 25 degrees Celsius. And then plus 0.1 times 900 gives us 90 joules per degree Celsius times T final minus 25 degrees Celsius. And it equals 0. So all three terms add up and equals 0. Now what? Now we have to use the distributive property. So the 19.5 is going to multiply by the TF and the minus 50. The 1,255.8 will multiply by TF and negative 25. The 90 will multiply by TF and the negative 25. So we are going to use the distributive property. And you can see I wrote the steps down. I find if I just punch it into my calculator, I am bound to make a mistake. So we can't really do any math with this part just yet, but we can do the arithmetic. So 19.5 times 50, 1,255.8 times 25, and 90 times 25. We can do that. So you can see we've still got the 19.5 joules per degree Celsius times TF. But the 19.5 times 50 becomes 975. And this plus sign at the end of the line is the same as the plus sign we had above it. The 1,255.8 times TF comes down, but the 1,255.8 times 25 becomes 31,395 joules. And then here's our plus sign. 90 times TF, and then minus 90 times 25, so that would be minus 2,250 joules. So now what? We can leave all the TFs on one side and take all those negative terms and add them to the other side. So the terms with TFs stay where they are. But the terms that were negative, the minus 975, the minus 31,395, and then minus 2,250, I add those to both sides so they disappear on the left and show up on the right as positive numbers. So on the right side, we'll take the 975 plus the 31,395 plus 2,250 and add all those up to make a single term. And on the left side, 19.5 times TF plus 1255.8 times TF plus 90 times TF. Add up all the numbers because they're all times TF. And so on the left side we have 1,365.3 joules per degree Celsius times TF equals 34,620 joules. Now to get TF all by itself, we divide both sides by 1,365.3. And we end up that our final temperature was 25.36 degrees Celsius. The math is not difficult, but the math is certainly tedious. And I find if I don't write down every step, I make a mistake. And it's annoying because it's not hard math. So don't skip steps. All right, let's talk about phase change and latent heat. A change in phase, remember phase is like going from a solid to a liquid or a liquid to a gas. So a change in phase requires a change in energy to break or form those intermolecular bonds. The energy does not give rise to a temperature change. So when you are boiling water, if you stick a thermometer in it, the water still stays at 100 degrees Celsius. Even though you're adding heat energy and you're making steam, the water does not change in temperature. That added energy you give it goes into breaking those intermolecular bonds and making the water molecules move away from each other. So now it's not a liquid but a gas. We give a special name to this energy. We call it the latent heat of fusion. That's what's required to turn 1 gram of substance from a solid into a liquid without a temperature change. So if you're melting an ice cube, for water, The CGS unit is 80 calories per gram, but the one we're going to use is 3.33 times 10 to the fifth joules per kilogram, because that is the MKS unit. That will be our MKS unit, our metric unit. So to turn a liquid into a solid, you have to remove heat energy, and that heat energy is given by the equation Q equals M multiplied by L sub F. L sub F is the latent heat of fusion, that 3.33 times 10 to the fifth joules per kilogram if we're talking about water. You would be able to look this up in a chart. You don't need to memorize it. And then M is the mass. Suppose we want to take a liquid and turn it into a gas. For that, you need the latent heat of vaporization. By the way, some books leave off the term latent and just call it heat of fusion and heat of vaporization. For water, that would be 2.26 times 10 to the 6 joules per kilogram. So to vaporize, Q is equal to M multiplied by L sub V, where L sub V is the latent heat of vaporization and M is the mass. We're going to look at a warming curve where this is drawn for 1 gram of ice at going from minus 20 degrees Celsius to steam at 150 degrees Celsius. So across the horizontal axis, we have across the horizontal axis, we have the heat input in joules, and on the vertical axis, you have the temperature in degrees Celsius. We are starting at negative 20 degrees Celsius. There's 0 degrees Celsius, 100, and 150. Across the horizontal axis, it's 0 and 41.8 and 374.8 and so on. So you'll notice this graph has an interesting shape. It has an inclined region and then a plateau, a horizontal part. It has an inclined region and then a second plateau or horizontal part. And then it has a third inclined region. So the inclined regions represent a single phase. On this one, because we're starting out cold and getting hot, we start out with a solid and then is a gas. The first incline is the solid region. The first plateau, where the temperature does not change, we're turning our solid into a liquid. The second incline, it's all liquid and we're changing its temperature. The second plateau, we're turning the liquid into a gas, no temperature change. And the last incline, we're taking that gas and heating it up. So you can see that phase transitions take place at a single temperature, so they're horizontal on this graph, and single phases are inclined regions. So let's look at the energy it took to do this and what other information we can pull out of this kind of graph. Suppose we want the melting temperature. The melting temperature and the freezing temperature are the same thing, and they are the lowest plateau. So the melting temperature is 0 degrees Celsius, which you knew for water. That is also the freezing temperature. So melting and freezing are that first plateau. They're both 0 degrees Celsius. The boiling temperature and the condensation temperature are the second plateau, and that's 100 degrees Celsius. So boiling and condensation are both the second plateau. They're both 100 degrees Celsius. So if I drew you a graph for a substance you did not know, a mystery one, just by looking at it, you can tell me what its melting and freezing temperatures are, what its boiling and condensation temperatures are. The heat of fusion, which is L sub F, we get it from the formula Q equals M L sub F. So we need to find heat of fusion is going from a solid to a liquid. So we look at the lowest plateau, heat of fusion, going from a solid to a liquid. And you can see our Q ends up at 374.8, and it starts out as 41.8. So 374.8 and 41.8. 374.8 and 41.8. So final minus initial. These numbers come from the graph. Equals the mass. We said it was 1 gram, so that is 0.001 kilograms. And then LCBF we do not know, but we want to calculate it. So you subtract the two numbers on the left and divide both sides by 0.001. And you end up with 3.33 times 10 to the 5th joules per kilogram. For the latent heat of vaporization, that's L sub V. It's Q equals M times L sub V. So we go back to the graph. Heat of vaporization is boiling. And that's this second plateau, going from a liquid to a gas. And you can see our Qs, we end up with, we've added 3,053.4 joules. And we started out with 793.4. So it's the difference in these two numbers, again, final minus initial. So 3,053.4 joules minus 793.4 joules equals our mass, which was 0.001 kilograms times L sub V. Do the subtraction, you get 2,260 joules, and divide both sides by the mass, and we end up with 2.26 times 10 to the 6th joules per kilogram. And now we can do our three specific heats. Specific heat is Q equals MC delta T. We get it from that equation. So for the solid, that's the first incline. For the solid, we'll use this area. For the liquid, we'll use the middle incline. And for the gas, we'll use the top one. So our Q starts out at 0 and ends 41.8. Our temperature starts out at -20 and ends up at 0. So specific heat, Q equals MC delta T. So 41.8 joules minus 0 joules equals 0.01. I'm sorry, let's try that again. 0.001 kilograms times C multiplied by 0 degrees Celsius minus -20 degrees Celsius. Don't forget that our starting temperature was a -20. So 41.8 minus 0 is 41.8. 0 minus -20, a minus makes it a plus, so it's a positive. And positive 20 times 0.001 gives me that 0.02. And when we do our arithmetic, it's 2,090 joules per kilogram degrees Celsius. If by skipping any steps I confuse you on the math, by all means, ask me about it. I can help you include the missing steps. And please don't skip steps unless you're good at it. For the specific heat of the liquid, we just move up to the second incline. Q is equal to MC delta T. 793.4 joules minus 374.8 joules equals 0.001 kilograms times little c times 100 minus 0. You do the math and you end up with 4,186 joules per kilogram degrees Celsius. Last one for the last incline portion, Q equals MC delta T. So 3,153.9 minus 3,053.4 equals 0.001 kilograms times little c times 150 degrees Celsius minus 100 degrees Celsius. And when you do the arithmetic, you get 2,010 joules per kilogram degrees Celsius. If I draw you a warming curve, you ought to be able to answer any one of these questions as it applies to that specific warming curve. All right, moving on. We're going to take an example, and it is going to have parts to it. So we have a 100-gram aluminum cup, 250 grams of water in it at 25 degrees Celsius. By now, you should realize that if you have a liquid in a cup, and I don't give you different temperatures for the cup and the liquid, you should assume that they have reached equilibrium and they are at the same temperature. So the starting temperature for the cup and the starting temperature for the water are both 25 degrees Celsius. If you add 50 grams of ice to the cup, what's the final temperature of the mixture? So we need to know the latent heat of fusion, 3.33 times 10 to the 5th joules per kilogram. That's going to be energy associated with melting that ice cube. We need the mass of the aluminum, the specific heat of the aluminum, the initial temperature of the aluminum. We need the mass of the water, the specific heat of water, the initial temperature of the water, mass of ice, specific heat of ice, initial temperature of ice. I will tell you something right now. Because they didn't give us an initial temperature of the ice, you need to assume it's 0 degrees Celsius. And in that case, we don't need the specific heat of ice. It's a trick to write it down. So, Q lost plus Q gained equals 0. We don't know what's gaining or losing, so we're just going to write everything down. So the Q for the cup plus the Q for the water in the cup plus the Q to melt the ice. When you melt ice, you've got water at 0 degrees Celsius. And now we want the Q to warm that 0 degrees Celsius water. So these last two terms relate only to the mass associated with the ice cube, not the starting mass in the cup. All right? The last two terms are all about the ice cube. So we have MC delta T for the cup plus MC delta T for the water in the cup, plus to melt the ice, that's M times L sub F, and again, it's associated with the ice. And then to take that melted ice and turn it into the same temperature as the water in the cup, that would be MC delta T for the melt water. Melt water is a term that people use for water that started out frozen. So in the wintertime, if your river gets its water from melting snow and ice, that water is called meltwater. We don't have a lot of that around here, so most of us are unfamiliar with it. So the water in the cup and the water associated with the ice cube are two separate things, and we do not combine them. Alrighty, so again, break it up. Everything gets its own line. That helps me keep my numbers straight. So the mass of the cup, MC delta T cup, so 0.1 kilograms. The cup is aluminum, so 900 joules per kilogram degrees Celsius times T final minus 25 degrees Celsius. Plus, now for the water, 0.025 kilograms times 4,186 joules per kilogram degrees Celsius times T final minus 25 degrees Celsius. Plus, to melt the ice cube, it's 0.05 kilograms multiplied by 3.33 times 10 to the 5th joules per kilogram. Plus, you have to take that little melted ice cube, that little puddle of 0 degrees water, and change its temperature. So 0.05 kilograms multiplied by 4,186 joules per kilogram degrees Celsius times T final minus 0 degrees Celsius. Why did I plug in 4,186 instead of 2,090? Because the 2,090 only applies if you've got a cold ice cube and you're making an ice cube at a different temperature. So if we had our ice cube at minus 15 degrees Celsius, then it would matter. But we don't. This is ice water at 0 degrees Celsius. and its final temperature is TF. Its initial temperature is 0 because it started out as an ice cube. In the step right above it, we melted it. Now we're changing its temperature. So now what do? We take the mass and the specific heat, multiply them together, leave the change in temperature in parentheses. So for the cup, we have 0.1 times 900, which will give us 90 joules per degree Celsius, times T final minus 25 degrees Celsius, plus, for the water, 0.25 times 4,186 gives you 1,046.5 joules per degree Celsius, multiplied by T final minus 25 degrees Celsius, plus the ice. Well, 0.05 times 3.33 times 10 to the 5th gives us 16,650 joules, plus 0.05 times 4,186 gives us 209.3 joules per degree Celsius, and T final minus 0 is just T final. Now we need to use the distributive property, so take these numbers and multiply them by what's in parentheses. And we have 90 joules per degree Celsius times TF minus 2,250 joules plus 1,046.5 joules per degree Celsius times TF minus 26,162.5 joules plus 16,650 joules plus 209.3 joules per degree Celsius times TF, all adding up to 0. We'll keep the TF terms on one side and add them up. And we'll take these non-TF terms and move them to the other side. So that minus 2250, we have to add 2250 to both sides. This minus 26,162.5, we have to add that to both sides. This is a positive 16,650. We have to subtract that from both sides. So on the left side, we have all our TF terms, and on the right side, we have all our just numbers. Now what do? We take the numeric coefficients in front of the TFs, so all the numbers in front of the TFs, and add them up. So 90 plus 1,046.5 plus 209.3, we get a single number times TF, and on the right-hand side, we just add the numbers up, do the math. So on the left side, we get 1,345.8 joules per degree Celsius times TF. And on the right-hand side, we end up with, I don't know why it's doing this, putting this little, on the right-hand side, we end up with 11,762.5 joules. To get TF all by itself, we obviously have to divide both sides by 1,345.8. We end up with 8.74 degrees Celsius. These are not hard problems, but they require paying attention to the details, people. Write out the steps. The tree is dead. It died for your education. Use the paper. All right. Two objects in contact are going to seek thermal equilibrium. The warmer object is going to lose heat energy. The colder one is going to gain heat energy until we reach thermal equilibrium. So let's talk about some methods that items gain or lose heat energy. One is by conduction. So conduction is the transfer of heat energy due to molecular collisions. Molecules slam into each other. So hot air blows on you and your temperature changes, or cold air blows on you and your temperature changes. Or hot air rises and cold air sinks. Your heat comes on at the baseboards and cold air at the ceiling sinks down, and you end up with some conduction. I'm sorry, that's convection. Conduction is molecules touching each other. So you're cold and your friend is warm. You hold hands, you warm up, they cool down. Or you're hot and you grab a cold soda from the refrigerator. As when you hold the can, there is conduction. Heat energy from your body warms up the can and you cool off. Conduction, transfer because of physical contact. We use it to calculate R values associated with home insulation. So the more insulation you have in your house, the less energy it loses. Or if you've got double pane windows, which most homes do these days compared to single pane, it makes a difference. You don't need to memorize this equation. I only mention it because I wanted to talk about this transfer. You'll notice that when we're talking about it, it matters what are the two temperatures. So if you're talking about your house, inside and outside temperatures, and it matters about the separation distance. So is it the heat energy going between a wall that's 8 or 12 inches thick or a pane of glass that's only a 1/4 inch thick? And it matters about the cross-sectional area. So houses with lots of windows in them usually transfer a lot of heat energy in and out because of those windows. The fewer windows you have, the less thermal energy you're going to lose. Alrighty. So there's a table in the book in chapter 14 for thermal conductivities. We will look at some of them. So we've got aluminum, silver, gold, copper, water, wood, and air. You don't need to care about the specific heats. I just wrote it down. You'll notice I used CGS units and thermal conductivity, and we do need to care about that. So the different objects have different rates of conduction. The faster an object takes heat energy away from you, the colder it's going to feel. All right, the faster it removes energy, the colder it's going to feel. When you touch a piece of metal, it almost always feels cool to the touch, at least right away, unless it's on the stove, obviously. But if you had a metal bar on the tabletop and a wooden pencil and a cotton scarf, they would all feel temperature-wise different to your hand. The metal bar would always feel colder. Maybe you know this, maybe you don't have a metal bar, but you have one of those really nice thermal mugs that are so popular these days. So it's made out of metal usually, and they feel really cool to the touch because they have a higher thermal conductivity. I know that sounds counterintuitive. We'll talk about how they work at the end of this section. So different objects, different rates of conduction. The faster it takes energy away, the colder it feels. So why does a tile floor feel colder than a wooden one? And why does a wooden floor feel colder than a carpeted one? Excuse me. Tile takes heat energy away from you faster than wood, and wood takes heat energy away from you faster than carpet. So the faster you lose heat energy, the colder something feels. Let's talk about thermal underwear. Thermal underwear has little pockets to trap air because air has a really teeny tiny low thermal conductivity. So if you can trap air between your body and the outside, you will lose less heat energy. It takes a lot longer. That's the principle behind dressing in layers also. So if you're worried about, if you're dressing for a winter hike, they tell you to dress in layers. And there are two reasons for that. One is that as you begin to exercise, you're going to warm up, and you don't want to get so warm that you sweat, because you then have moisture against your skin and you run the risk of hypothermia that way. So dressing in layers traps air. and that helps slow down the release of heat energy to the atmosphere. So polar bear fur, you may not know this, but polar bear fur is actually the little bits of hair are hollow, like a soda straw, and that's to trap air. Feather fluffing, if you've ever noticed a bird, when a bird is cold, they fluff up those feathers, and the feather fluffing is there to trap air to help keep you warm, or the bird warm. If you have a down jacket, it's the same principle, traps air. So conduction, we want things that don't conduct very well if we want to maintain a temperature. Convection, that's hot things rise and cold things sink. So that is the molecular motion of the mass movement of molecules. So conduction was collision. Convection is the mass movement of molecules from one location to another, and it's to transfer heat energy. So hot materials rise, cold ones sink. In a room, you have, if you live in an area where heating is important, you put your heating vents at the floor because hot air rises. If you live someplace where air conditioning is mostly what you do, then you have your vents at the ceiling because cold air sinks. In a perfect world, the heat would come out of the floor, the air conditioning would come out of the ceiling, and everything would be wonderful. But that's not perfect. We usually pick one and stick with it. So in Florida, you have a lot of your vents coming out near the ceiling. And the farther north you go, the more likely you are to find your vents at the floor. So let's talk about wind at the beach. So hot sand during the daytime, colder water. Hot air rises, so the air over the sand rises up. The air over the water is cooler. It's going to swoop in and take that hot air's place. So during the daytime at the beach, the wind primarily seems to blow from the water towards the land. And at nighttime, the opposite is true. At nighttime, the sand doesn't feel hot anymore, but the water is still warm. So hot air rises over the water, cool air sinks over the sand, and now the wind has switched directions. Which means if you're sailing, you have to be careful at twilight when the sun goes down, because winds oftentimes switch rather quickly if you're not careful. Radiation is the transfer of heat energy through electromagnetic radiation. It's the only heat transfer that does not require a medium. It does not require molecules. So conduction requires molecules. Convection requires molecules. Radiation does not require molecules. The sun's energy reaches us through radiation. A thermos bottle. Thermos is a brand name, so technically you'd want to call it a vacuum bottle. Reduces the loss of heat energy by cutting down on conduction, convection, and radiation. So conduction, that's actually the vacuum. On a good thermos, or on those really high-tech insulated glasses we can buy these days, the inside and outside walls are actually, there's a vacuum. The air has been sucked out, and that vacuum means that there aren't any molecules, so you won't have heat loss due to conduction. The stopper in the top cuts down on convection, no hot air rising, no cold air sinking into it. It's just trapped. And then if you pay attention to it, the lining, the inside surface is a silvered lining, and that reduces radiation loss, because any radiation hits the silvered lining and bounces back in, hits the silvered lining and bounces back in. And that stops the chapter. We'll do something else in our next video.